Have you ever really looked at a simple pill? I mean, it seems so ordinary, right? But what if I told you that locked inside that tiny tablet is a fascinating story, a story of intense pressure, invisible forces, and a delicate dance between being tough as nails and dissolving on command? And it all begins right here. Just a loose collection of powders, maybe some tiny granules. But how in the world do you get from this shapeless dust, to the solid uniform pill that we all recognize?
That's the real trick, isn't it? A pill has to be strong enough to get tossed around during manufacturing and shipping, but at the same time, it's designed to break down perfectly inside your body. It's this amazing balancing act, and today we're going to dive into the physics that make it all possible.
Okay, so to really get what's happening on a microscopic level, we first need to learn the lingo. Don't worry, it's not that complicated. It really just boils down to 3 key ideas that describe the whole process.
First up, we have compression. This one's pretty straightforward. It's just that initial squeeze. You apply pressure, and you force all the empty space, all the air, out from between the individual powder particles. Next, there's consolidation. Okay, so the air is gone, the particles are now smushed right up against each other. This is where they really start to interact and build strength. It's the stage where that loose powder actually starts to become a solid.
And finally, you've got compaction. This is the big one, the umbrella term for the whole shebang. It covers everything from that first squeeze of compression to the final strength building of consolidation. In short, compaction is the entire journey from powder to pill.
So let's actually follow that journey. We're going to zoom in on what happens inside the machine's mold, which in the industry they call the die. This is where the magic, or, well, the physics, really begins.
And here's our roadmap. Now, this all happens in the blink of an eye, but every single particle goes through these critical stages. They rearrange, they deform, they bond together, and then they have to survive the perilous escape from the die. So the very first thing that happens under a little bit of pressure is just a big shuffle. Think of it like a jar of marbles. If you pour sand in and give it a shake, the sand fills all the empty gaps, right? It's the exact same idea here. The smaller particles wiggle their way into the spaces between the bigger ones. But once there's no more room to shuffle, the particles themselves have to change shape. This is called deformation. Now, some of it is elastic, like a stress ball. You squeeze it, and it bounces right back. But the really crucial part is plastic deformation. This is more like modeling clay. The particles get permanently squished into a new shape, which means way more surface area is touching its neighbors, and that is key.
And all that new contact, that is everything. Because now, with all these particles pressed tightly together, we've hit the most critical moment, the actual fusion. We're talking about turning millions of individual grains into one single solid object. How on earth does that even work?
Well, one theory is pretty simple: mechanical interlocking. The idea is that the particles bend and deform so much that they just get tangled up with each other, kind of like puzzle pieces locking together. And yeah, this definitely happens, and it adds some strength, but it's not the main event, not by a long shot. A much bigger deal is something called intermolecular forces. You see, under that insane pressure, particles can actually break apart, creating brand new, perfectly clean surfaces. And when these new surfaces get super close to each other, tiny attractions called van der Waals forces kick in. The best way to think about it is like millions of microscopic magnets suddenly switching on, all pulling the particles together into one solid piece. And for some materials, there's another awesome mechanism at play: solid bridges. In powders like aspirin, for example, powerful hydrogen bonds can form, creating these literal, super strong bridges connecting the particles. In other materials, the pressure at the tiny points of contact can get so intense that it actually melts a little bit of the material, creating a liquid film that acts like glue and then instantly re-solidifies. How cool is that? Okay, so the pill is formed. The bonds are forged. You'd think we're done, right? Nope. The story is far from over. Now comes one of the most dangerous moments in a pill's life: getting out of the die in one piece. I mean, just imagine it. You've just been squeezed with thousands and thousands of pounds of force, and then, in an instant, it's all gone. What happens in that split second is what determines if you have a perfect tablet or just a pile of dust. The second that pressure is released, the tablet goes through what's called elastic rebound.
Remember those particles that deformed like a stress ball? Well, they all try to spring back to their original shape at once. This creates a massive amount of internal stress that's literally trying to tear the brand new tablet apart from the inside out.
And if that internal stress wins the fight, the tablet will fail. The two classic ways this happens are called capping, where the top of the tablet just pops right off like a bottle cap, and lamination, where the whole tablet splits into separate layers, kind of like a piece of plywood. And here's the kicker. As the tablet is getting pushed out of the die, it's still facing friction from rubbing against the die wall. That friction, combined with that sudden release of pressure, can create forces that are stronger than the bonds we just worked so hard to create. If those bonds break, the tablet fails. Game over.
But when the formulation is just right and the physics are perfectly balanced, the tablet survives this gauntlet. It survives the pressure, the bonding, and the release, and it emerges whole. And just like that, the transformation is complete. What was once just a random collection of individual particles is now a structured, bonded solid. It's strong enough to travel across the country, but it's also designed to break apart exactly when it's needed.
So, the next time you hold a simple pill in your hand, maybe take a second. Think about the incredible journey of forces it survived to get to you. It's a tiny marvel of engineering, a perfect example of that delicate balance between strength and purpose that makes modern medicine even possible.